You might have heard someone say an algorithm is O of n or O log n, but what does that actually mean? Simply put, Big O notation is a way of using math to describe how efficient an algorithm is. It tells us how quickly the running time will grow as the amount of data increases. Now, you might wonder, why not just run the program on a computer and see how long it takes? The problem is, run times can be affected by many outside factors: your computer's hardware specs, whether the CPU is busy doing something else, how the operating system schedules tasks, or even how many apps you have open in the background. Because of these variables, the same algorithm could give very different timing results on different machines or with different data sets. Big O, on the other hand, looks at the efficiency of the algorithm structure itself. It's completely independent of hardware or operating system conditions. Think of it like taking an X-ray of your algorithm. You can see how it will behave with large amounts of data without even running it, and that makes it incredibly valuable for spotting performance issues early. In Big O analysis, we mainly focus on two things. The first is time complexity, which is how the running time changes as the input size n changes. The second is space complexity, which is how much memory the algorithm needs, and that can also change with n. For example, one algorithm might run very fast, but use a lot of memory, while another might use very little memory, but take longer to run. This is where we need to make trade-offs when designing algorithms. So why should you learn Big O? If you're preparing for job interviews, algorithm complexity questions almost always come up. If you're a developer, understanding complexity helps you write more efficient code and avoid system crashes when handling large datasets. In fact, many performance bottlenecks in real-world systems happen because complexity wasn't considered during design. Common complexity classes include constant time, O of 1, logarithmic time, O of log n, linear time, O of n, linearithmic time, O of n log n, quadratic time, O of n squared, and even exponential time, O of 2 to the n, or factorial time, O of n factorial, which grow explosively. The difference in their growth rates is huge. In upcoming videos, we'll explain each one in detail, with examples, and how they're applied in real development and interviews. In short, mastering Big O is the foundation of learning algorithms and data structures. It helps you think like a professional engineer, writing not just code that works, but code that stays fast and stable even when the amount of data becomes massive.